Okay, variables, parameters, and constants. So let's review what we just talked about, what you read, and what you had in your top hat questions. First of all, variable. There's two aspects to it. It is a letter, or it could be a notation, right? There could be more than just one letter, and we'll see that later in class. But primarily, it's a letter or some kind of symbolism, for it taking on a value of a changing quantity in a given situation. So two aspects to a variable. It's a letter or some type of combination of symbols, and that letter or that symbol takes on the value of a changing quantity in a given situation. Okay, so related to that is a domain. So if you have a variable, then it has a domain, and that domain is a set of all possible values the variable can take on as it's changing in the situation, right? We said the value of the variable is changing, so the domain is what are all possible values that changing variable could take on. So that's a domain. Okay, so then we said a parameter next. A parameter also has two main points to it. Again, it's a letter. If it's not a letter, it's not a parameter. If it's not a letter, it can't be a variable. Okay? It's a letter. And then a parameter, its value stays constant within the given situation. So within whatever situation you're looking at, that letter stands for that constant value. Now here's the key to a parameter. This is the key you got to learn. It's not just a constant and then you don't think about anything else. Here's the key to a parameter. All right? In a new situation, the parameter could take on a different constant value. So in this new situation, it's still going to be constant, but that letter could be a different constant. So from situation to situation, a parameter, yes, it can change, but within a situation, it stays constant. And then last is a constant. A constant is a value that never changes, ever, no matter what the situation is. So it could be represented by a letter or a number. Here's some examples. The speed of light, that's a constant. The mass of the moon, okay, that's a constant. All right. This number E, you may have seen this. It comes up in logs. It's the natural base. It's the natural base. It comes up in financial, compound interest, and exponential growth. Okay, it shows up in exponential growth. This is it never changes, no matter what your situation is. So those are some examples of constants. Okay, so yes, we can imagine a scenario where the mass of the moon might change. Like it gets hit by a giant meteor, or something. We come up with these kind of fantastic situations. But is it appropriate to say that the mass is a parameter or a constant? A constant. Okay, so for given situations, mass of the moon is staying constant. So it's don't get too crazy in imagining situations where you could change something. If that's, I'm trying to distinguish between parameters and constants. Okay, what's their question? Someone starts. Okay. Questions on these definitions? So we need practice. We need practice of this. So here's a situation. A circular pond for raising fish has a depth of 5.4 feet and a radius of 28 feet, and it was filled at a rate of 70.9 gallons per minute. The volume of the cylinder is pi r squared h. So I have 9 items here, and your task is to determine if it's a variable, a parameter, a constant, or none of the above, and explain why. So you're going to work on these 9. Each one of these 9 is either a variable, parameter, constant, or none of the above. So it takes a few minutes to work on these. Think about them by yourself. I would always encourage you to talk amongst yourselves, ask questions with one of us. Okay, go. See how you did. See how you did. Number one. What do you think number one is? Parameter. Number one is a parameter. Why? Because it's a letter that stands for something that won't change in this situation. The capacity of that pond won't change. Pi. Yeah, that's a real common constant, right? Pi is the same no matter what situation we're in. Okay? 5.4 feet, the depth of the pond. Parameter? None. Parameters are letters. Okay? Yes, it's a constant in the situation, but it's not a letter. So the parameter, it would be the letter that stands for that. So we could say D equals the depth in the pond. And that now D is the parameter. But just 5.4 feet, that meets the criteria of a parameter, except for it's not a letter, so it's not a parameter. Okay? R, the radius of the pond. That's a parameter, right? Because we've got that letter, R. Okay? Number of fish in the pond. None. It's closest to what? It would be variable, right? So it would be none because there's no letter. But if we said F was the number of fish in the pond, then F would be the variable, taking on the number of fish as that changed. Okay? The height of water in the pond in feet, H. Some of you are saying variable. That's right. This is a variable. Okay? Because we can say was filled or is filling, doesn't matter. It's the height of that water is changing, right? The height of the water is changing. Okay? Volume of the water in the pond in feet cubed, V. Another variable. Okay? 32.17 feet per second, the acceleration of gravity. Constant. Do we need a letter? No. There is a letter, G. Usually lowercase g is that constant. But even so, just the number itself, we still say it's a constant. And finally, 17.9 gallons per minute, the filling rate. Lots are saying none. What's it closest to? Variable or parameter? If we assigned a letter to it, say K. If we said K was the filling rate, would that be a parameter or a constant in this situation? Sorry, variable or parameter? Parameter. Okay. So I said was filled. You just take the wording at its word that it's staying at this constant rate of 17.9 gallons per minute. Okay. So don't argue against the problem and say, well, it would be impossible to truly fill it at 17.9 gallons per minute. It's got to vary a little bit. Well, yeah, that's true. But just for the sake of what's being given here, we're just assuming it's constant. And so if we assigned a letter, that 70.9 gallons per minute filling rate would be a parameter. But it's not because there's no letter. Questions on these items? Yes, please. Why is 3 not a constant? Why? Okay, great question. Why is 3 not a constant?
It's not a letter because it can change in the next situation.
Yeah, so another pond would have a different depth. So it's not. So constants never change in the whole universe ever in time, right? So this, you take a new situation with a new pond, it has a different depth. So it would be only a parameter if we put a letter on it. Good question. Other questions? Okay, so now, for each of those that is a variable, I want you to figure out what the domain is. Remember what the domain is. It's all possible values of that variable. And then for each one that's a parameter, what's the value of, so that's only going to have one value. What's the value of that parameter? So for let's see, for variable, we got 6 and 7. For parameter, we got 1 and 4. So for 6 and 7, find the domain. For 1 and 4, identify the value of the parameter. Go. So what did you find for the capacity of the pond, of the parameter, right? So that's going to, in this situation, that will stay constant at what value? V equals what?
21,168 over 5 pi feet.
Okay.
Or if you want the equation,
13,000. Is it you get 13,000 also? Whoever was saying that? 13,000. And that's in feet cubed? But then we could just use, if we're working in the situation, we can know what that is, or maybe not. So whether we know what that value is or not, we can still represent it with capital V, and that's usually the reason for parameters is that you might not know the value, but you know that it's a constant in the situation, and so they're going to use that capital V in writing other expressions and other equations. Okay, next one, the radius of the pond. R. Too easy, right? Given. 28 feet. Okay? So the height of the water in the pond in feet is a variable. So now we're talking about the domain. All possible values would be, what's the lowest? So oftentimes when you're doing a domain, you're gonna identify the lowest possible value and the highest possible value, and it'll be everything in between. And that's not always true, but that's common. And this is one example of that. So what's the lowest value of H that it could be? You could have 0, right? You could have 0 feet of water. So here's one way to write that domain. You could write it with inequalities. And what's the highest it could be? 5.4. Okay. Another way to write that would be, since we're including the endpoints of the interval, we could use brackets. So we could go 0. So this would be 2 ways to express that domain. All the numbers between 0 and 5.4, including 0 and 5.4. Should be easy. Okay, then volume of the water in the pond. I won't write it, but it'll be the same kind of answer, and we'd go from what to what? 0 to the 13,000, right? It would be the same exact type of answer as 6, but it would be 0 to 13,300.2. Or, to make it easier, what could you write? You could write 0, comma, V, capital V, right? So this is perfectly fine. We defined it as that value. So you could define the domain for little v as from 0 to V, including V. And that's a lot easier to write. Okay, questions on this slide? Domain, parameters, variables, constants. Okay, so whenever we come to real-world situations, we're going to start by understanding the situation and then assigning letters that are parameters or variables that haven't been given to us in the situation. Okay, so this idea of this kind of thing, assigning meaning to different letters as variables, parameters, identifying constants, is going to be a really important first part of just understanding the problem and organizing the information. Okay, we want to do that every time. Okay. All right. So let's move on and start talking about. Did you read about functions for today? Okay, so just a few brief notes on functions before we talk about notation. So a function is a special relationship between two quantities. We may or may not to get today to the special relationship because we've got other stuff, but we will talk about what makes it special coming soon. But in general, it's a relationship between two quantities. What do we mean by quantities? All the stuff we're talking about: volume, temperature, weight, speed. Those are all quantities. So when you have two of those two variables changing together, two quantities changing together, like speed and time, or distance and weight could be varying together, you might have a relationship that's a function, right? Or a relationship of those two quantities. So if you're ever asked to describe a particular function, the correct response would be to identify the two quantities that the function is relating. It's a question I ask my students in office hours all the time, and they just kind of go, oh, I don't know, I'm just reading this thing here. This function, I'm just reading it. Well, what is it about? It's always about some relationship between two quantities. So if you're just asked to describe a particular function, or you're just identifying what that function is, that's about identifying the two quantities that are related. Okay? One of those is independent and the other is dependent. So one of those we think of changing just on its own, independently, and the other one changes dependent on the value of the first one. Okay? So tell me about this function. What's it about? Oh, it's telling me what the temperature is, in a certain location, dependent on the time of day it is, or the number of minutes after noon. So my dependent quantity would be the number of minutes after noon, and then my independent quantity would be number of minutes after noon. My dependent quantity would be the temperature at that location. So temperature depends on the time. So temperature is dependent, time is independent. Okay, and so then what we're going to focus on today is functions have special notation, which is essential to understand because it's going to show up in so many of the things that we do. When we're writing expressions and formulas and equations, this function notation is going to be prevalent, and you can't hesitate when you look at it. You have to know what it's about. Okay, so that's what we're going to work on today. Function notation and what it is. Questions on this? Just some bullet points on functions. Okay, so here's a situation. The distance a motorcycle travels from an intersection in miles is a function of time elapsed since leaving the intersection in minutes. And so we'll name this relationship G. So this G, I'm not using it as a variable or a parameter, but I'm using it to name this relationship between distance the motorcycle has traveled from an intersection and the time elapsed since it left the intersection. Right? So I want you to look at something here. When you look at that, what comes to mind? What do you think when you look at that? So think to yourself. Don't verbalize yet. So when you see this notation, so this is all semester, this is going to be hugely important that we know exactly what we're looking at when we look at something like that. Okay, so as you reflect on your thoughts about what you saw, what you thought, did you see possibly like something of a command to do something? Is that part of what you thought? A command to do something. Okay, so yes, that is a common kind of actually misconception about what this means. This is not a command to do something. Here's what this is. When you see an expression like this, the goal is that you can see that there's really three things all together, three things in harmony. First of all, the whole thing is a value of the dependent variable. And I'm going to say this a million times, because when other things start coming into the picture, this is quickly forgotten. Function notation, first and foremost, is a value of the dependent variable. And so what would that be? The dependent variable here is the distance the motorcycle has traveled. So that's a number of miles right there. That G of 8.3 is some number of miles from the intersection. It's a value of the dependent variable. Okay, that's part one. So it's a value of the dependent variable of a function whose name is G. Again, G is not a variable. G is not a parameter. Now we're using this letter to signify just a name for the whole function. It represents the whole function. And what's the last part? So which value of the dependent variable is it? It's changing, right? The distance the motorcycle is from the intersection is changing. So which distance is it? It's the distance when 8.3 minutes have gone by since the intersection. So now it's the value of the dependent variable, number of miles, when the independent variable is 8.3, a number of minutes. So G of 8.3 is a number of miles. Which number of miles is it? It's the number of miles the motorcycle is from the intersection 8.3 minutes after the motorcycle left the intersection. So why do we have function notation when we could just use y, right? Because you're used to x being the independent variable, y being the dependent variable. Why use this when we could just say just y? Well, this tells us a lot more, right? You see? What is it telling us? So it's telling us the value of the dependent variable, but it tells us what the name of the function is. So that's going to be important if we have more than one function that we're dealing with at once. But it also tells us which y value it is. It tells us the particular y value when the value of the independent is 8.3. In this case, 8.3 minutes have gone by. So it's a lot more informative than just writing y. Is there a question? Or you good? Okay. Doesn't make sense. So, the first and foremost is the green. That when you look at that, you see that's standing for a particular value of the dependent variable. In fact, that whole thing is, it's a value of the dependent variable. Yeah. Okay. So here is a function f of x equals 3x squared plus 8x minus 17. Same question. When I put up f of 2, what do you think? Now it's telling you to do something, right? Now it means to do something, whereas before it didn't. What do you think? Yeah. Right. So that's what I'm getting at. No! It still doesn't mean to do something. It still doesn't mean to do something. First and foremost, what does it mean? First and foremost, that represents a value. We could just leave it like that. We don't have to plug anything in. It still has a valid meaning. What's its meaning? It's the value of the dependent variable of the name of the function f when the value of the independent variable is 2. You don't have to plug 2 in. You could just use f of 2, and it has the same meaning as whatever that number is. Now, if we want the value, if we want the number, yes, we do something. But the key is that when you see f of 2, you don't think, oh, that's telling me to do something. You think, oh, that's just representing a value, a number, whether I do something or not. And so, what value does it represent? Some of you couldn't stand to not do it, right? What is it? 11, okay? So yes, f of 2 is 11. But whether we know that it's 11 or not does not make that expression f of 2 any less meaningful. Anywhere that we would put 11 because it's f of 2, we could put f of 2. And it would still mean that value of the dependent variable and the independent variable has value of 2. Okay, any questions on that? So that's going to take practice to break. So if you have this immediate knee-jerk response of that means plug and chug, that means do something. We want to break that and change our thinking to that just means a value of the dependent variable when the independent variable is 2. Yeah.
Is it still okay to write f of 2 is equal to 3x squared plus 8x minus 17, or would you need 2's and 3x?
Yeah. No. F of x equals that. So we're going to talk about that in a second. But no, f of 2 does not equal the 3x squared plus 8x minus 7. F of 2 would equal, you could write that expression with the 2's plugged in. Yeah. Okay, other questions? Okay, so here's some more terminology now related to functions. So suppose given two quantities represented by y and p, so I have a function that relate y and p. Suppose that p is a function of y according to this. So here's some questions. Where in the above statement do you see the function definition, the dependent variable, the independent variable, the function name, function notation, the function rule, and the value of p? So see if you can work through these quickly. Where in this above statement do you see all those things? So if some of them we haven't talked about, you might just make a guess or kind of deduce what you think it is. Others you should know. But I've got these two variables y and p in relationship, and this function is modeling that relationship. So now where in the above statement? So you're picking pieces of, or the whole thing, to answer these different items. You're taking a part of or all of this to answer where you see these particular things. Take a minute. Go. So again, if you didn't know all of these, it might be that not all of these were in the reading, and so not all of them you know. That's okay. But the function definitions. Anyone know where in that statement do we see the function definition?
P is a function of y.
Okay, so the function definition is the whole thing. That is the function definition, okay? So the function definition is the whole thing. It has everything involved in it, okay? So it's defining that function called z. Where do we see the dependent variable in that statement? Where do we see the dependent variable? Okay, someone said left of the equal sign. The function notation, z of y. Z of y. Which is also called what? P, right? So our variable, P is a function of y. It means P is dependent on y. So P is dependent. In the function definition, though, there's no P, right? So it's z of y. That's what z of y is. It's P. Okay, the independent variable. That's y, right? We see that on both sides. We see that in the function notation, and we see that over here on the right too. The function name, easy, z. Function notation. That's right. Function notation gives is z of y. It always gives the value of what? Dependent variable. Function notation always represents a value of the dependent variable. That's a key for today. Function rule. What's the rule? It's the part that tells you how to get values of the dependent variable. So that's the right-hand side. 3y squared plus 8y minus 17. That's the rule. The rule tells you how to get values of the dependent variable. Where do you see the value of p in that expression? Z of y. Z of y. Questions on those? So the definition is the whole thing. It's the notation and the rule. The function notation along with the rule gives you the whole definition. Notice that's z of y. That's our dependent variable. We call that function notation, and in this case, it's the value of p. Z of y. Any questions? Okay, what about this? Is z equals 3 a valid statement? Is z equals 3 a valid statement? People are saying no. What is z again? It's the name, right? It's the whole function. It's the name of the whole function. It doesn't take on values, okay? So Don't do that. But then what would kind of, if you saw that and you saw someone in error doing that, what would you think they meant? So correct it. What's intended by the statement z equals 3? Write it in two other ways correctly. There's actually three different ways you could do it. There's actually three different ways you could do it. If you get two, that's good. Two different ways to write this, what was intended by this. Okay, what's one way? Someone said P equals 3. Is it right? Yes. But more importantly, the most important way to change this would be to what? Z of y. Z of y equals 3. That's the one I want to make sure you get. That's the way to express a value of the dependent variable being 3, not z. Z just is it's a label. It's a name that just means the whole function. It doesn't take on values. Yes, ma'am. Anyone got the third way? Yes, sir.
They could have been trying to say z of 3.
Nope. Well, yeah, maybe. Yeah, yeah, that's true. That's true. Yeah. Yeah. So if you had 3 equals the rule, right? So if 3 equals the rule, then that's also equal to the value of the dependent variable. Okay. But this is the one. We don't want to do this. Instead, we want to do this. That's the key. Okay, we need practice. Practice. Here we go. Any questions on that? What? Because if P is a function of y, I'm defining P as a variable. P takes on values. But in a function definition, that letter is not a variable. It's the name of the function. It never takes on values. That's the way function notation works. What about y equals 3? Is that the same thing? Does that mean the same thing? So they're both valid statements. Do they mean the same thing? No, because now you're saying that the value of the independent variable is 3 versus the value of the dependent variable versus 3. So we don't know. So by z equals 3, our best guess is that they want to say that the value of the dependent variable is 3. We don't know what they're thinking. But our best guess is they mean the value of the dependent variable. Like, yeah, okay. If you say y equals 3, then maybe that's what they were thinking, but just as long as you know, that means that the independent variable has a value of 3. So these are not the same. Other questions? They're both valid, but not the same. Okay, so we want to work on this. Don't try to copy all this down, just your responses. You can look at the video later. Okay, let t equal a time elapsed in seconds since a car began moving after a pit stop, a race car. Okay, d is the distance in feet traveled by the car since it first started moving. Okay, so we want to think of the relationship of d as a function of t. The distance from the pit stop is a function of time since being at the pit stop. Okay, so if that's so, then you're just going to answer these questions. A, which is dependent, which is the independent variable, and then you're going to use the function named w, represent the distance d at any number of seconds t using the function named w. And then once you get that, check, make sure you got 1b is crucial, that you can get 1b correct before moving on to number 2. Something of t, that's something. Okay, you should be on number 2 now. You should be on number 2. W of t. That's what you should have had for distance from the pit stop. W of t. So you could write W of t or d equals W of t. W is the name of the function that gives distance for time elapsed, then it's W of t is equal to d. Okay, make sure you're working on number 2. So now here we're going to use function notation to represent these different values. So all of them are going to involve, all these are going to involve that using the function notation, W of something, or expressions with W of something. Check with us. Make sure you're doing it right. Check with us. What's the first 4-second time from what to what? Regroup. Let's regroup here and talk about 2D. So for 2A, this is just asking you for a value of the dependent variable. We can represent that as W of 9. W of 9. It's just asking you for a value of D. The particular value of D when 9 seconds have elapsed since the pit stop. Okay. The next one, the change in distance, you recognize is going to be a final value of distance minus initial value of distance. We've seen that before. So our D final, W of 5, D initial, W of 2. Okay? And then C is just like that. You just have to figure out what the starting and ending times are. So it's the second 4-second time interval would start at 4 and end at 8. So that would be W of 8 minus W of 4. Okay, so now this next one's a little tricky, but important. So it's also a change in distance. So what will the general structure of it look like? The same as these, right? It's going to be W of a final time minus W of an initial time, because it's still a change in distance. It's going to be D final minus D initial. So we just got to figure out, according to this, what it's saying, what is the initial and final time? So maybe we'll start with the initial time. What's the initial time? X. So where does that go? First or second? Yeah, so X is going to go here, right? Because that's the initial time, just like the ones above. So now we want the change in distance over the 7-second time interval. So what if the time starts at X seconds, then how much time has elapsed 7 seconds after X seconds, or 7 seconds later? X plus 7. How many got it before I started it? How many got it before I started it? Does it make sense? Okay, so the quiz on, listen, don't pack up too quick so we can hear. The quiz on Thursday is on constant rate of change, like a lot like the homework and our top hat stuff today. And then it's also on all of today's stuff, including this last worksheet. So great practice for we did get to go over 3. Great practice for the quiz then. Would also be go over 3, go over that with another student or a TA or myself. So this is all fair game for the quiz as well. Beginning of class, written quiz. And then also check Blackboard for homework also. Check Blackboard. That'll be up by 4 o'clock today.